Hi, my name is Jesse Henrikson, and I'm the Vice President of Engineering at Lincoln Technology Solutions. Today I'm going to be talking about OLED burn-in and system-level techniques for reliable embedded OLED displays. OLED technology continues to expand into medical, industrial, automotive, avionics, and other embedded applications because it offers excellent contrast, fast response, wide viewing angles, and strong image quality. At the same time, embedded products can place very different demands on an OLED than a television or smartphone. They may display static graphics for long periods, operate at elevated temperatures, or remain active for thousands of hours. Today, we'll look beyond the general term burn-in and discuss how panel technology, compensation, host controls, user interface design, and validation can work together to improve long-term OLED reliability. Let's begin with a quick overview of the topics we'll cover. We'll organize the discussion into 4 sections. First, we'll define OLED aging and explain why embedded usage is different. Second, we'll look at why OLED reliability is improving through better materials, tandem structures, and compensation algorithms. Third, we'll discuss system-level prevention, including brightness control, pixel shifting, user interface design, thermal management, and digital deburn-in compensation. Finally, we'll review LTS test results and show how an embedded 4K 60 Hz platform can provide both high-performance video delivery and OLED operating policy control. Let's start by examining the operating conditions that make embedded OLED applications distinctive. The first section establishes the technical foundation for the rest of the presentation. The important point is that OLED aging is cumulative. It depends not only on the display panel, but also on what content is shown, how brightly that content is shown, the operating temperature, and how long particular pixels remain active. That becomes especially important when we compare consumer and embedded usage. Consumer OLED products normally show dynamic content. A television changes scenes continuously, and phones and tablets switch between applications, pages, and brightness levels. Embedded systems can behave very differently. A medical display may show the same control regions throughout an entire shift. An industrial HMI may keep status bars and alarm icons in fixed locations for years. Cockpit, automotive, and instrumentation displays may also contain persistent graphical elements. That means certain physical pixels experience more stress than others. The lifetime question is therefore not simply whether the OLED can display the required image, it's whether the complete system can manage that image over the intended operating profile. Static regions, brightness, color, temperature, and operating time all combine into a cumulative stress history. Before discussing how to manage that stress, it helps to define what people actually mean when they say burn-in. The term burn-in is often used to describe several different effects. The first is temporary image retention. A faint previous image may remain visible for a period of time but can fade after the content changes or the panel recovers. The second category includes short-term electrical or thermal effects. Recent drive history and temperature can temporarily affect uniformity. The third and most important long-term issue is permanent differential aging. This occurs when pixels accumulate different levels of stress and lose efficiency at different rates. The panel may still operate normally, but areas that were used more heavily may no longer match surrounding areas in brightness or color. System-level measures can reduce, redistribute, or delay that uneven aging. They can't fully reverse permanent degradation of the OLED materials. So what determines how quickly that differential aging develops? There are 5 primary factors. Brightness matters because higher luminance generally requires greater pixel drive. Static content matters because the same physical pixels carry the load repeatedly. Color matters because red, green, and blue subpixels can operate at different efficiencies and can age at different rates. Temperature matters because elevated panel temperatures can accelerate degradation. And finally, duty cycle matters. Even a moderately bright static element can become significant when it remains visible for thousands of hours. The practical risk model is therefore a combination of content profile, operating environment, panel compensation, and host system policy. Looking at only peak brightness or only total operating hours gives an incomplete picture. The positive news is that OLED technology itself is also improving. In the next section, we'll look at the technology changes that are improving OLED lifetime and reducing the visibility of image retention. There are three particularly important areas of progress. Modern OLEDs are becoming significantly more durable. First, improved emitter materials and optimized device structures can produce a given luminance with less electrical and thermal stress. Second, tandem OLED structures use multiple emission units. Rather than relying on a single emitting structure to provide all of the optical output, the load can be distributed across multiple units. This can improve efficiency, brightness capability, and operating lifetime. Third, compensation technology continues to improve. Aging models, electrical sensing, factory demura, calibration, and firmware correction can reduce visible non-uniformity as the panel accumulates operating time. These developments mean that burn-in performance shouldn't be judged only by the behavior of older OLED generations. However, better durability doesn't eliminate the importance of use case. Embedded products can still expose a panel to unusually static and high duty cycle content. Prevention therefore preserves and extends the benefits provided by better materials, tandem structures, and compensation. That brings us to the central theme of this presentation. Reliability must be managed at the system level. In this section, we'll separate the responsibilities of the panel from the responsibilities of the host system, and then look at the practical techniques available to both. The first distinction is panel level versus system level mitigation. Panel level controls can include pixel aging models, factory calibration, electrical or optical compensation, internal maintenance cycles, and panel-specific drive limits. The system designer may not have direct access to every one of these functions, but needs to understand what the panel already provides. The host system controls a different set of variables: brightness policy, thermal limits, pixel shifting, user interface movement, screensavers, standby behavior, usage tracking, and application-specific display modes. These two layers are complementary. Panel compensation cannot fully correct for an interface that keeps a bright static element in the same location indefinitely. At the same time, host software can't replace the electrical and optical compensation built into the panel. Reliable embedded OLED design is therefore a coordination problem. One important example of panel or controller-based compensation is digital deburn-in, or DBI. Digital deburn-in compensation begins with the content being displayed. The system estimates how much stress each pixel or region accumulates over time. That information is used to update a lookup table or aging model. The correction data can then adjust pixel luminance to reduce visible differences. A typical validation process begins by measuring initial luminance in defined regions of interest. The panel is then operated using either accelerated stress patterns or real-world representative content. At specified intervals, a neutral gray field is displayed and luminance is measured again. The resulting decay behavior is modeled and compensation coefficients are applied. The key point is that DBI is not simply a cosmetic image filter. It's a measurement, modeling, storage, and correction loop that must be validated over a long operating period. DBI can reduce visible non-uniformity, but the host system can also reduce how much uneven stress is created in the first place. Host-side prevention works by changing how long, how brightly, and where static content appears. Content motion includes pixel shifting and subtle movement of graphical elements. The movement may only be a few pixels, but it distributes stress across a larger physical area. Drive reduction includes brightness limits, inactivity dimming, screensavers, and low-stress standby states. Reducing luminance when full output is unnecessary lowers accumulated drive stress. Telemetry-aware policy makes these behaviors more intelligent. Temperature, operating hours, user activity, and system state can determine how the display behaves during active operation, idle periods, or standby. The goal is not to make mitigation obvious to the user. It's to reduce or redistribute stress while preserving the intended experience. Many of these strategies are most effective when they're considered during user interface design. A useful first step is to classify interface elements. Some elements must remain static because they're safety critical or essential to usability. Other elements can move slightly without affecting the user. A third group can dim, disappear, or time out when the system is inactive. Designers should also reduce unnecessary stressful patterns. Large static white regions, highly saturated permanent icons, and sharp fixed boundaries can create localized aging. Dark backgrounds, semi-transparent regions, subtle movement, and consistent dimming behavior can help the interface age more gracefully. A simple risk map, like the example shown here, can identify which areas require motion, dimming, or timeout policies before the UI is finalized. We'll now move from design principles to LTS implementation and measurement evidence. This final technical section connects the prevention methods we've discussed with measured data, embedded architecture, and validation strategy. We'll begin with results from LTS burn-in testing. This chart compares delta luminance after 3,000 hours under two different content profiles. The static stress pattern represents an accelerated and intentionally severe condition. Under that profile, the measured delta luminance remained below 3.5%. Under more real-world representative image and video content, the measured difference was approximately 1.5% after the same 3,000-hour period. The measurement process compares luminance inside and outside defined regions of interest using neutral gray screens to make aging-related differences easier to detect. Extreme static patterns still produce measurable differential aging. Real-world representative content produces substantially less variation. Ongoing LTS testing has now continued beyond 8,000 operating hours. This supports two conclusions. Modern compensation is effective, and the content profile and system behavior still have a major influence on the amount of stress the display accumulates. The next question is where the host controls and telemetry needed for these policies actually reside. LTS has developed an advanced embedded platform for 4K video at 60 Hz that can coordinate both video delivery and OLED operating policy. The platform uses a modular system-on-module and carrier board architecture to deliver 4K graphics and video at 60 Hz. The SOM provides reusable computing, memory, graphics, and operating system resources. The carrier board handles panel-facing interfaces, inputs, outputs, power sequencing, and application-specific integration. Beyond the high bandwidth video path, embedded Linux can expose controls for brightness limits, idle modes, thermal thresholds, pixel shifting, and maintenance routines. The platform can also collect temperature, brightness state, operating time, and other telemetry that supports application-specific OLED policies. The important technical achievement is not only stable 4K video output, it's the ability to combine high-performance video transport and OLED-aware system control within the same embedded architecture. Having those capabilities is valuable, but they still need to be validated against the real operating environment. A validation plan should represent the actual product usage rather than evaluating the panel only under generic laboratory conditions. Accelerated stress patterns remain useful. They reveal susceptibility and provide a worst-case reference. Real-world representative content is equally important. Actual user interface screens, video loops, operating modes, and duty cycle models often predict field behavior more accurately. System telemetry should be recorded alongside image quality measurements. That includes brightness state, panel temperature, operating time, standby behavior, and software policy state. A complete data package might include delta luminance, color difference, or delta E, white point, power, temperature history, and the status of mitigation policies. This links the visual result to the operating conditions that created it. The correct policy will also depend on the application. There is no universal mitigation profile. Medical applications may prioritize predictable brightness and color accuracy. Mitigation must not alter diagnostic content or introduce unexpected visual changes. Industrial HMIs often have long static operating periods, so inactivity dimming, screensavers, pixel shifting, and low-stress idle states may be appropriate. Automotive and avionics applications add wide temperature ranges, sunlight readability, safety-critical graphics, and complex power state transitions. Portable products benefit from a lower average brightness because it reduces power, heat, and pixel stress simultaneously. Premium consumer-like interfaces are naturally well suited to OLED's contrast and dynamic image quality, but persistent loops and navigation elements still require lifecycle review. The operating policy must therefore be derived from the product requirements, not simply copied from another display application. To make that process practical, we can reduce it to a short design checklist. During architecture development, the team should answer 6 questions. Which regions of user interface remain static, bright, or saturated? What luminance is actually required in each operating mode? What panel temperatures will occur in real use? Which compensation functions are provided by the panel and which must be provided by the host? Can the software track usage and consistently enforce the required policies? And finally, what luminance, color, and visibility thresholds define a successful lifetime result? The best time to answer these questions is during architecture and interface definition, not after image retention becomes visible. I'll close with 3 key takeaways. First, OLED technology is stronger than ever. Improved materials, tandem structures, and compensation algorithms are improving lifetime, brightness, efficiency, and burn-in performance. Second, embedded usage is different. Static interfaces, long duty cycles, and demanding thermal environments can still create difficult aging profiles. Third, prevention is a system-level responsibility. Content design, host behavior, panel compensation, telemetry, and validation must work together. When modern OLED panels are combined with thoughtful system engineering, they can deliver premium image quality in demanding embedded products. Thank you for watching. We hope this presentation provided a useful framework for thinking about OLED reliability as a complete system design problem rather than simply a panel characteristic. Lincoln Technology Solutions works across display design, supporting electronics, embedded solutions, optical performance, and product integration. We welcome the opportunity to continue the technical discussion.